Hello, this is Paul from Foresight Tech. In this lecture, we're going to find the limit using continuity. That we have a very important result here. We call the continuity of basic functions. And the results tell us all basic functions are continuous on their domain, including the power functions, root function. You remember this we learned before, and we also use optional and the data definition prove the power and the root function continuous before, right? Okay, and later we have results. After this, I will going to show you. And the polynomial is a combination of the power function. So combination of continuous function are continuous. The later I will going to show. So if power function continuous, so polynomial functions are continuous. And also rational function is what? Is the quotient of two polynomial functions. Okay, is the combination of continuous functions, so rational function also continuous. And the trig functions for the continuity we were going to discuss in the future topics. Okay, and for exponential function we're also going to discuss in the future. Okay, because we need other results. And the inverse function, inverse trig function is the inverse function of trig, right? Logarithmic function is the inverse function of exponential. We have another result in the book, okay, called if the original functions continuous, so the inverse functions also continuous. I will not give you complete proof here. Okay, so you have all the detail in the textbook. I will going to show the idea, okay, how to give intuitive proof. Okay, we're using graph. We think about the graph of the original function and the inverse function. Okay, remember they are symmetrical about the y equals x, right? So if the original function is continuous, which means no gap, so the image or the symmetric, the inverse function also, the curve of the inverse function also no gap or no hole, which means continuous, right? Okay, so if trig is continuous, that the inverse trig is continuous. If exponential continuous, so the inverse, which means the logarithmic, also continuous. Whatever, so far we have all these results. Okay, all the basic functions are continuous in the domain. Let me see here. This is one result that we just discussed. We call the continuity of combinations, and states as this: combinations of continuous functions are continuous. Okay, what the combination? The basic combination we have this: the sum, okay, added together, add two continuous function, we get a continuous function. Difference, subtract, product, or also we have the scalar multiplication. A function times a scalar number, of course, that's a continuous. And the product, if f is continuous, g continuous, the product is still continuous on the domain. And another is quotient. See, that's the basic, right? If we put the sum and the difference and the scalar multiplication together, sometimes we call the linear property. Okay, as the limit law we learned, linear property. So here I give one proof. So we look at the one proof is the sum. Okay, so all the others are very similar. Let me see how to prove the sum. So here I already showed. If f of g continues at a, at x equals a, and then the sum is also continuous. How to prove this? How to prove a function is continuous at a? Do you remember we have 1, 2, 3, right? First, define. Of course, we can't define. The second, then you define the limit, and later we're going to find the limit. And then the third, we're going to look at, check if the limit equals the value of the function at a. Definitely it is. Okay, so we can say f plus g is continuous. Let me go in step by step. So here at the beginning, right, we look at the limit of the function at x. Function as x approaches a. So what is the definition of the sum? The sum is the sum of the two functions. Okay, that's the basic definition. Do you remember? So this is the sum law we learned before. If the limit of the sum equals the sum of the limit, right? Because we know the limit exists. See, because f of g continues at a, so the limit exists. The limit exists, so the limit of the sum exists. It's just added them together. We call the sum lot, and then the limit of f at x approach a when x approach a is fa, because f continues. So this step is the continuity, and the g is the same, and the fa plus fg put together is the sum, right? The sum of function at a, that's the definition. And from the beginning to the end, we can see what, okay, the limit exists, and also the limit equals the value of the function at a. Therefore, f plus g is continuous. Okay, so this question we don't need to use epsilon delta definition. Okay, for all the other combination is the similar. You can kind of prove by yourself. And then we have another result. We got the composition. Okay, can you see? Continuity of a composition. And this result is even more important. So, because most of the function we look at is compositions. Okay, composite function is not just like a simple combination. What are these results? It results as compositions of continuous functions are continuous on their domain. For example, I give f is continuous, g is continuous. If we composite both functions together, we get the composite function is continuous. These results set. Or if we state as a theorem, is like this. Okay, if g is continuous at a, and f is continuous at ga, and then f composed with g is continuous at a. Okay, of course g is the inner, right? So if we go back to review a little about the composition function is this. Okay, and a is in the original domain, g mapping a to ga, the inner function, and the second step f mapping ga to the final y, right? Y, which is f at ga. Okay, so two steps, which means g is the inner, f is the outer. So we finally get a composite function. See, if the inner function continues at a, the outer function is continuous at ga. So the composite function is continuous at the original x equals a. How to prove this? Let me show. This time we have to use epsilon delta definition. You will see this is a powerful tool. It's not so complicated. I did not show example before for this type, so be patient with me. All we need to do is prove this theorem. If this theorem is true, so this result is true, right? Let me show here. All we need to do is what? Okay, all we need to do is to show this limit equal this, right? If this limit equal this, and this result shows what? Shows the function, the composite function is continuous at a, right? The limit exists, the limit equal the value of the function. Okay, of course we know how to define. Definitely is defined. So how to show this? Epsilon delta definition. Wait, let me show a little. We're going to do this question, so you will build the experience for epsilon delta language. Okay, so do you remember the definition? A limit equal this number, which means what? Given any epsilon greater than 0, we need to find a delta, right? If x go into the delta neighborhood of a, and then the value of the function goes into the epsilon neighborhood of this b. Do you remember this, the definition? Which means f can approach this as x goes sufficiently close a. This is epsilon delta. Now, you know what we need to do. We take a little bit of time to explore. Do you remember two steps to prove, right? The first step is find this delta. The second step is write everything down. This is the basic. How do you find the delta is do this. We need to explore. Okay, need to check this inequality going to do this, use this inequality to find what is data. If we find that's what we proved. Okay, so how to do? Explore this. What is the composition? First, I will write the definition. So you will see. Wait. Okay, so this one is equivalent to this: f parenthesis gx minus the absolute value, and then minus f g a parenthesis less than epsilon. Remember the definition, right? Okay, and then from here a little bit, because it's complicated, we don't like this, so we simplify. If you set up gx is y, and we set up ga is a number b. Okay, so this we can simplify to another format. Keep in mind our purpose is going to find out what is data. Okay, that's all we need to do. So this number simplify a little is f y minus f at b, right? Absolute value less than epsilon. Think about this. If I say this is 1, okay, the first inequality, we have this. Can we explore this? See, you should be familiar with this. F going to the neighborhood of fb. Okay, this is what? This is true because we have a result. The function f, the other functions continues at b. If it's continuous, fy will approach fb, which means what? Okay, so we're going to write this because we are familiar with this. From here, we will try to find the data. Is do this way because f is continuous at b, right? Do you remember f? The other function is continuous at ga because this b is just ga. Okay, so we have these results. We have the limit of f equals the value of b, which means given epsilon, okay, the epsilon already given, we can find the data. But this data is not this data, so I use another name. I said we exist. This means exist. Exist data 1. And if y go into the data 1's neighborhood of b, which means this y minus b absolute value less than data 1. Okay, and then what do we have? And then the first, this one satisfied. That is good because f is continuous. So for any epsilon given, we can find the data 1 if y go into the data 1's neighborhood of b, which means y approach b, and then fy will approach fb. That's the continuity. Okay, from the first continuity, good. We found this, but this is not we need. We need the data. Okay, we need the data. Data is the neighborhood of a. Okay, so we link it to the neighborhood of x of a, but this time is not x, is still y. One more step, a little bit explore. Which one we need? Almost think about this. Think about this part. Data 1 given epsilon, we know data 1. Data 1 is a number. What is this? Think about it. And this is what we need. I change this one to here, equivalent to, because y is gx. If I wrote it in another way, so you will see it clearly. Wrote it this way. Y is gx, b is ga. Can you see something? And less than data 1. And if I say this is the second, we should be familiar. What? This is a link to this. If data 1 is given, no matter how small the number is, this means what? Gx approach ga, right? Can gx approach ga? Yes, because g is the inner function. Because g is continuous at a, we're going to follow these ways. Okay, so that means this is true. We know this is true because this is true, then we can find something. Find what? Find data that we need. Rod complete here is what? Is because no, this time not f, is g is continuous at a, at x equals a. Let me highlight this. Okay, this is continue the continuity of the outer function, continuity of the inner function we're going to use, and then this time exactly does data. Can you see? Given data 1, can gx go into the data 1's neighborhood of this? Yes, because g continues at a. Therefore, we have this exist data. This time, given data 1, we exist data. Like this, given data, given epsilon, we find the data. Okay, you can imagine this is epsilon. Just imagine. Okay, this is any small number of epsilon. Even given, can x go into the GA's epsilon's neighborhood of GA? Yes, because G is continuous. So exist data if if what? If x approach a, x minus a less than this data. If x approach a, then this approach this, right? Okay, which means then the second is true. See what do we get now? Okay, we get here. Imagine this is the most important. We already find the data. Okay, why? Let me go back a little bit. We already find the data. Okay, why? You can imagine, given any epsilon greater than 0, can we find the data? Yes. I have to go backwards. We find the data. If x go into the data neighborhood, then the second, so this inequality is true. If this equality is true, means this inequality is true. If this is true, then the first is true. The first is what we need to prove, and which means this is true, right? See, if we go backwards, definitely. Okay, so put everything together. I already wrote for you. I hope you get it. So this is the basic ways of how we can prove this kind of stuff. Okay. Let me see. I already showed here. Okay. So a little bit. Do you remember how did we say? Given any epsilon, remember, so GA we said is P, right? Since f is continuous, the outer is continuous, so given this any epsilon, we can find the data 1. That's what we explore. So find the data 1 first. And y going to the data 1's neighborhood, then fy going to the epsilon's neighborhood, okay, of fb. That's the continuity. And then, because data 1 is given here, since the continuity of G, okay, yeah, that's true, right? So for the given data 1, for this given data 1, we can find the data such that if x is going to the data's neighborhood, and then G will going to the data 1's neighborhood of B because of the continuity. So you can see, I put these two together, remember? So did the first, did the second, we just explore. The first, the second, put these together. Combine the above using y equals gx, of course. This y is gx. And then we have these results. If x is going to the data neighborhood of it, because we find the data already, okay? See, exists the data. And if x is going to the data neighborhood of A, and then you can imagine, if x is going to the A, if this is true, then this is true. If this is true, and then move to here, this is true. Why? Because G is Y. If this is true, and then this is true, that's the final one we need, right? Okay, upper log. Y is Gx into here, and the B is Ga into here. Okay, so can you see? That's what we get. We get Fy minus Fb less than epsilon. This is what? This is the epsilon data definition. See, if x approach A, then Of course, this is the composite function of f composite of g. So f compose g approach to f compose g at a, approach to a. Can you see this? That's the limit. Therefore, what? Using the Epsilon data definition, f compose g is continuous. So can you get this? Is exactly what we explored before. It's just like this. Okay. And we have the major results here. Now we have the results. We call it direct substitution property. Do you remember? We learned the direct substitution property for this property works for polynomial, right? Now we can extend this property, okay, for all the continuous function. The result is here. If f is continuous on its domain and x equals a is on the domain, and of course then f is continuous at a, right? Then f continues at a, we can directly substitute y. That's the definition. That's the definition. Okay. What? This means that the limit exists and also the limit equals the value of the function at a. If we have this, okay, so this is the major one we're going to use. I have one example to show you. All we need to do, look at this, directly substitute this x by a, replace x by a. When we can replace, all we need to make sure is f continues at a, or usually we break it down into two steps. So first, f is continuous on its domain, okay, and using like the combination, composition, like that, okay, basic function, and then we make sure a is on the domain. Two steps, okay. These are questions. This looks complicated, so imagine what the results we have learned. Is this a basic function? No, it is not a basic function. If we know this basic function, that's continuous on the domain, right? But we know this is a composition, okay? It's a composite function, but a little bit complicated composite. Can we see? I'm going to show here. This is a composite. Is a composite of continuous functions. Can we see? And later I will going to decompose it. Okay, so you can see it clearly. This is a composite. It's a composite function. Okay, of continuous function. Continuous. If this is true functions, a continuous function to composition, we get a continuous, right? So the first, why this is a composite of continuous function. Let me write this for you. Decompose. We learned this decomposition before, right? So I was going to say this is y. The function I say is y. So we have y. I was going to decompose 3. I will set up all this is u. Okay, 3. Put it the use power. I replace the power by u. This is a simple function. And the second u is root function. Okay, is a square root of, I put a v here. So this is root function, simple, right? However, one more composite. What is v? V is a polynomial. So v is x squared minus 2x minus 4. Good. Can we see? This is a composite. So of course we compose twice, okay? And the exponential function compose a root function and then compose a polynomial function. You know, exponential is a basic function, continuous, right? Root function, continuous. Polynomial function, continuous. Therefore, the composition function is continuous. So what do we get? We say this. And now we get a we get a fx, which means this, okay, is exactly y, is 3 raised to 2. Can you see this? X square minus 2x minus 4. This is a complicated function. Don't worry, is continuous. This is the major one we need. Is continuous. Is continuous. Of course, it's on its domain. Our results tell us composition is continuous on the domain. So now, what is the domain? Is 4 on the domain or not on the domain? That's the major one. We have to solve the domain. How to solve? This root function, okay, square root, something under square root should be non-negative number, right? So we have to do this. We need to solve, and all these terms, x square minus 2x minus 4 greater than or equal 0, of course. And if you solve this, then we get the domain. Okay, we will get the domain. I think you know how to solve this, right? This is a quadratic inequality. All we need to do is do this. All we need to do is do this. Okay, this is a quadratic function. A is 1 greater than 0, so it's open up. And then you can find that this is 2, 0. And can you look at it? If we find it, the first 0, 1 minus 5, the second 1 plus 5. Of course, we have a lot of ways. You can use a quadratic formula, or you can make a perfect square to find this 2. I ignore this step. I already found this number and this number. So what is the domain? The domain greater than 0. So negative infinity to this number, or this number to positive infinity. Why? Because of the value, y value greater than 0, right? Okay, so I put here. So I already solved. So get the domain is this one. We just said is from negative infinity to 1 minus square root of 5. Okay, because this is equals 0, so I have to do this. I have to put the close, okay, break it, or another break it. 1 plus square root of 5 to positive infinity. You know how to do this. I get the domain. Now, what do we see? How about the 4? This number is 2 point something, 3 point something. 4 is bigger than this, which means 4 is in the domain, right? Okay, so now, so what do we get? Definitely. So we get 4, or x equals 4 is on the domain. Now we almost right. See, and the function, the bigger function continues, and then f. Okay, this a is in the domain, so f is continuous at 4. Therefore, what we can do, direct substitute. So we made everything ready, okay, for the substitution. So now what do we do? Directly substitute. Okay, all we need to do now is what do we have? So I wrote a little one more step. What we wrote, just the function is this: x squared minus 2x minus 4 is continuous, right, at x equals 4, because the function continues on the domain. 4 is on the domain, so this is continuous. This is continuous, we can use direct substitute. So by we say direct substitution property. Okay, we put it, and then we will have this, and the limit. All we need to do is find the limit. Okay, the limit x approach 4. This function, copy here again. x squared minus 2x minus 4. How do you do this? This is the final. Now, directly substitute. Okay, what it means direct substitute? Directly substitute this 4 into this x, replace x by 4. Therefore, we have this 4 squared minus 2 times 4 minus 4. See, this direct substitute do calculation, so we will easily find the results. So that's 3 squared, and which means 9. Okay, that's all. Thank you.